Before I introduce Lorenzo and he goes for this talk, let's shortly hear from Olivier about JUICE and what has happened in the past year. Venus flyby, for example, here.
So Olivier Witasse, project scientist of the JUICE mission. So just a quick status report on the project. So the spacecraft is nominal. We are at 1.2 astronomical units from the sun. In fact, as Martin mentioned, we flew by Venus in end of August and everything went fine, perfect navigation. So we are on track for the next flyby, which will be a flyby of the Earth end of September 2026. I'm pretty sure we'll come back to that at some point in 2026. The highlight of the recent weeks was certainly the campaign of observation of the interstellar object 3I Atlas that took place in November. So for 3 weeks, we took data with the 5 instruments and with the navigation cameras that are on board the spacecraft. The data will come only end of February. Due to the low bandwidth, it takes some time to get the data on ground for this period of the year. So we have to wait until end of February to get the data. But as a teaser, we released 1 image from the navigation camera last week, so you should be able to find it on the web. I think it's a great image. So please have a look. And other than that, last month we met with all the JUICE scientists. We meet usually twice per year, and we had always good discussions. And in particular, we discussed a possible flyby of a Calico Ray moon, which is a very small moon in the Jovian system. And next year we will decide whether we would like to perform such a flyby. That should be also an interesting discussion and hopefully an interesting milestone of the mission. And with that, I leave the floor back to Martin and Lorenzo.
Thank you very much, Olivier. I will now introduce Lorenzo. So Lorenzo Bruzzone, he is a professor at the University of Trento in Italy, and he's there the founder and director of the Remote Sensing Laboratory in the Department of Information Engineering and Computer Science. His research interests, as we will hear much more about today, are in remote sensing, radar science, signal processing and machine learning. He has an extensive publication record in this field, and he has received many awards as well for his work. He is currently the principal investigator of the Radar for Icy Moon Exploration, or RIME, for JUICE, and of the Subsurface Radar Sounder, SRS, for Envision. He is the science lead also of the Stratus mission concept for radar sounding of the Earth from space. And he will, in his talk, combine these two elements, combine Earth observation and Jupiter observation, and talk about that. So without further ado, Lorenzo, the floor is yours.
Thank you very much for the introduction, and good afternoon, everybody. It is really a pleasure to be here with you to present some of the activities that are related to radar sounding. As it was mentioned in this presentation, I'd like to focus the attention not only on the Jovian Icy moons that are the target of the RIME radar, but I'd like to start the presentation pointing out what it has been done by the community for Earth observation of the icy targets. So that what we can do is to understand a little bit better what is the experience that we have on the ice on the Earth, and how we can try to exploit this experience then later on for the icy moons. So you can see that the structure of my presentation will start just recalling some simple background concept of radar sounder, just to be sure that everyone is at the same page on this kind of instruments. I don't enter in the details, I just share the main concept. And then I'd like to show how these instruments have been used for taking information on the polar region of our planet. Illustrating some example of data acquired that I think are quite inspiring from what we can expect to see then when we will be on the icy moons with the RIME radar. Of course, RIME will be a part of this presentation in the second part of this talk, and I'd like to show you what are the main science objectives that we have and give you some information about the radar, some challenges that we have. and then also show the first data that we have acquired during the LEGA, the flyby of the moon and the first flyby of the Earth. And then I'll conclude the talk. Well, I think that just to introduce the topic, if you are not familiar with the radar sounder, we are talking about a special kind of radar that transmit with a geometry, which is a geometry nadir-looking, low-frequency electromagnetic waves. These electromagnetic waves propagate to the surface of celestial body, and they are partially reflected by the surface, and we can receive the reflection by the receiver of the radar, but partially then they propagate into the subsurface, which means that every time that we have an interface in the subsurface, we get other echoes that are received and measured by the receiver. Typically, what happens is that these echoes are generated by change in the composition, the material that we have in the subsurface, by mechanical interfaces or interfaces in terms of thermal interfaces. And measuring this kind of echo that we receive from the different position in the subsurface, we are in the condition to construct what we call the radiograms that represent in section what we have in the subsurface. Now, these kind of instruments, as you probably know, have been widely used already in other space missions, but the origin of this kind of technology is for Earth observation since the 60s. Here you can see just some name of systems that have been used for Earth observation. Typically, what it has been done was to take data only by airborne platform or helicopter. We don't have yet any kind of mission from space with this kind of instruments. I'll talk about this later in my presentation. But as you know, we have a sounder on board of spacecraft to Mars. We have Marsis and Sharad. And before that, we had the first sounder that was on board of Apollo mission for studying the subsurface of the moon. And there is then another sounder that has been active on the moon more recently. And then, of course, we have the activities that are connected to JUICE for the exploration of the icy moons. But, you know, we have also the Europa Clipper mission with another sounder, which is called Horizon. I'll talk a little bit at the end of my presentation of that. And there is another instrument in progress in the development phase on the Envision mission to Venus of ESA that is expected to be launched in 2031. Now, in my presentation, I'll focus my attention on the observation of icy targets. And so I focus my attention on what it has been done and is in progress for Earth observation. And then I try to connect this with what we expect to do when we'll be on the Jupiter icy moons. Well, I was mentioning before on Earth, we have a long experience of performing measurements on the polar areas with this kind of radar instruments. Here you can see just the name of some very important systems that have acquired, are still in some cases acquiring data on the polar caps of our planet. What we do is, of course, to get information on the mass of ice that we have in Antarctica and in Greenland, taking advantage from the capability of this radar to get the interfaces that we have in the subsurface. So we are in the condition in which what we can do is to extract a lot of relevant information for the characterization of the ice sheet and the ice shelf. I would like to show you some examples. I think they help to understand what we can do, and they can help us to understand what we can expect to do when we'll be on the icy moons of Jupiter. I start just illustrating a little bit more in detail how the process works. This is an animation that helps to understand, where you can see the process of transmitting the electromagnetic wave toward the surface of the mass of ice and the process of reflection. Then, taking into account the movement of the platform and the delay of the echo, we can construct these radiograms. This is an example of radiograms acquired in Antarctica, where you can see the bedrock and you can see the layer of the ice. Now, if we focus a little bit more on some specific cases, it becomes quite interesting to see how we can get information on the column of ice with this kind of radar instruments. This is a nice example. This is an illustration that represents one interesting area in Antarctica where we have the very popular, let's say, well-known Lake Vostok. We are in an area where we have that on the top of the bedrock, we have the column of ice, but at the interface between the ice and the bedrock, we have a large lake. And this is an area that is widely studied. We are in the condition in which here there are also drilling activity for getting detailed information on the column of ice up to the bedrock and the water. Now, if you look at this scenario, in these areas, we have a lot of data that have been acquired by the sounder. And this is an example of radagrams that represent the section in one portion of this area, where you can see a lot of features that are extremely interesting that allow to study what is happening not only at the surface, of course, and at the bedrock, at the interface between the bedrock and the ice, but in all the column. You can see all this layering, which is due to the different age of the ice with different kind of interfaces. You can see at the interface between the ice and the bedrock the presence of the lake with a strong reflection that represents the surface of the water. But then we have the capability to measure what is happening on the bedrocks in the side of the lake. We can measure different kind of reflections that are associated with the created ice. And then when you look at this radiogram, you can see also the deflection of the layers. That is something which is due to the presence of the water at the interface that reduce the stability of the column of ice. So, of course, this is an example, but it's an example that points out that it's possible to extract relevant information on what is happening in the subsurface, in this case, in the Antarctica. Then, when you take this data, you can have radiogram that are represented in different ways. This depends on the instruments, but you are in the condition in which you can start to extract a lot of information that for Earth observation becomes extremely important. For example, for monitoring the status of the ice, but also for monitoring climate change. You can extract the information on the thickness of the ice. You can, of course, characterize the condition of the ice at the bedrock. This can be done and can be done now also by using techniques that are automatic, that help us to analyze the large amount of data that have been acquired by the different campaigns that have been implemented with different kinds of systems. This is just a representation of different acquisition during one of the campaign, during a flight, where you can see the representation of the column of ice, the bedrock, and of course, the 3D structure that can be extracted by analyzing all this data and by processing through interpolation. We have now capability for this kind of data to perform automatic analysis. That is, we can, for example, extract automatically the position of the bedrock. We can extract information on the layering and on the surface. And this is something that enables the capability then to reconstruct the properties in the volume that is taken by this radar sounder that just acquired in sections. You can see here, for example, the use of interpolation techniques, geospatial interpolation techniques based on kriging that allow us to reconstruct the height of the surface and the topography at the bedrock. And then when you have this kind of information, you can generate a map that represent, for example, the ice thickness and estimate the ice thickness with the spatial distribution that come from the analysis of the data. Now, these are just examples to say that we are in the condition in which we can extract a lot of information. And I'd like to show you another example that I think is quite interesting because we present a more complex scenario where we have on the left the floating ice, the ice shelf, that is the ice which is on the top of the ocean. And on the right, we have the transition to the grounded ice, the ice sheet, where you can see the interface is represented by the rocks. So analyzing the data, we can detect, of course, these kind of interfaces. We can detect also the basal crevasses that are associated with the presence of the ice. We can detect the crevasses that are associated with the ice also connected with the surface. Then we have all the layering that can be extracted. So you can understand that there are many data available that provide very important information and also teach us to understand what we see in the subsurface in presence of different conditions, water, different conditions on the ice, rocks, and so on and so forth. Now, on this kind of data, we have also the capability to extract the information, not only just analyzing the data visually, but we start to have the capability in the community to extract automatically the information from the data. That is, this is an example of a long radiogram where we have the transition from the ice shelf to the ice sheet. And this is a kind of manual annotation of the different parts of the radiograms that represent the inland ice, the floating ice, the bedrock, and so on and so forth. This is a manual annotation. This is what you can get if you use automatic techniques that are based on machine learning, in particular on deep learning strategies. Which means that we have the capability to analyze what is happening in these interfaces. And thanks to the many data that we have for Earth observation, we are also able now to learn machine-based techniques to recognize the different kind of interfaces that are associated with the different conditions that you have in the subsurface. Well, I show you another example that is still related to Earth observation, not this time on the polar caps, but these instruments are also used for monitoring the glaciers. Here we are in an area which is in the Dolomites, in the Alpine area, close to our city in Trento, where we have the glacier which is called Marmolada, quite a big and popular glacier in this area. And you can see acquisition taken from an helicopter. This is the trajectory on the data that characterize the subsurface of the glacier. This in the middle, you can see just the camera that take images of the glacier. What you see on the left is the subsurface. And these are data taken by the radar sounder, and that represent the structure of the bedrock of the glacier. But what you can extract is also information related, for example, to the presence of water. This is important for studying, of course, the status of the glacier. It's also very important because the presence of pockets of water at the base of the glacier can create collapses of the mass of ice. We had a terrible accident a few years ago that affected people that was due to a collapse of a part of the glacier that was not predicted because there were no data that pointed out the presence probably of a pocket of water at the base of the ice. But it's just to show you another kind of example. Now, on Earth observation, we have a lot of data taken by airborne systems, but we still have the problem that up to now, it was not possible to develop a radar sounder working from space, from satellite. We have for the moon, we have for Mars, but it's challenging to implement for Earth observation. This is something which is critical because despite we have many data available, we have still large gaps in Antarctica and Greenland. And these are extremely critical for understanding completely the real situation of the ice. Here you can see some maps that represent, for example, the level of uncertainty that we have in the representation of the ice thickness in different portions of Greenland and Antarctica. we have uncertainty that are larger than 600 meters in some areas, which means that a lot of the uncertainty also on the estimation, for example, of the potential effect on the sea level rising. And then the data that we have available anyway are taken by different systems, are taken, of course, with different conditions. We don't have regular data. We don't have regular sampling of what is happening in the different season to the ice. So there are currently activities in progress to design missions that are for Earth observation. One of these missions is connected with the study that are done with ESA for the development of the Stratus concept. Stratus is the acronym of Satellite Radar Sounder for Earth Subsurface Sensing. This is not an approved mission, but there are many studies now in progress for enabling the possible implementation of a mission like this. The idea is that with this kind of satellite capability, also for Earth observation, we could address a lot of very interesting science objectives. Of course, we are in a condition in which we can fill all the gap related to the study of the ice sheet thickness. We can study the topography, the basal topography. We can try to understand the status of the ice from the surface to the bedrock, which means, for example, try to get information on the melting of the ice near the surface. This is extremely critical because you are in the condition in which the melting percolate waters and reduce the stability of the ice. All this has impact on the melting of the ice, and of course on the possible effect on the sea level rising. And with this kind of data, we will be in the condition to have a complete mapping of the subglacial lakes and channels. Subglacial lakes are again important because they create a kind of lubrification between the bedrock and the ice that is critical when you try to project then this in sea level rising and so in the effect of the climate change. And of course, many other kind of study can be done related also to the floating ice. Now, I don't have time to enter in the details, but there is a lot of work that has been done for maturing this kind of concept. And so we have also a lot of techniques now that support the understanding of the interfaces in different conditions in the column of ice. This means that we are in the situation in which we can use this knowledge that has been developed for studying the ice on the Earth, also translating this on what we will see on the icy moons. So there is a lot of connection between what we are doing on the Earth and what it will be possible to understand on the icy moons when we arrive in the icy moon. Now, just a couple of words to say what is the reason for which we don't have any radar sounder operating from space around the Earth, which sounds quite strange since we have operating on other planets. There are three main reasons that create challenges. One is that, of course, on the Earth, we would like to have data with high resolution. The resolution that typically we get for the sounder that explore other celestial body is not enough for getting good data on the Earth, where we'd like to have much better characterization. And this implies to have a very large antenna that are difficult to implement from the mechanical perspective. Then a second problem on the Earth is the ionosphere that creates a significant distortion that becomes very critical, especially when you try to get high resolution data. And there is then a third point that has been very recently solved. That was that up to a couple of years ago, it was not possible to operate this kind of radar because there was not a frequency allocation. The rules does not allow to transmit at the low frequency that we need with this kind of sounder. Now, fortunately, this has been fixed and there is an allocation. And so it becomes possible to move ahead with a mission like this. To get the allocation took about 15 years, which is a very long time because this is a very complex process. Now, just to show you what is the idea that can help to simplify the mechanical problems with large antenna, the idea is to use a sounder which is based on a flying formation with a main satellite that transmits the signal, and then in the flying formation, 4 different sensors that collect the echoes and simulate an antenna which is longer. In this way, it's possible to better control the resolution and to better control the clutter. Now, this is a polarimetric system, and it will operate between 40 and 50 megahertz. So at frequency that are similar to the one of the data that I have presented in my previous part of the talk. With this kind of system, we expect it's possible to reach the bedrock everywhere in Antarctica and in Greenland, and so to have a big picture of what is happening there. Of course, with respect to the data that we get from aircraft, the quality of the radiograms will be slightly reduced. Of course, we are from space, we have different constraints, but some simulation that have been carried out point out that we still get all the information on the features that are in the subsurface of the ice that we need in order to have then all the scientific objective reached. Okay, having said that, I'd like to move now to the Jupiter icy moons. The experience that we have gained on the Earth is extremely relevant for understanding what we can do on Europa, Callisto, and Ganymede. And in this case, it was already mentioned in the introduction, what we have developed is the radar for icy moon exploration system. This is just a simple animation that in synthesis just represent what I already illustrated before, but just in connection with a possible flyby of Ganymede. We have a 16 meters antenna that transmits the pulses toward the surface of Ganymede, and then we expect to have the echo coming from the surface and the subsurface. Our target is to have a penetration that is in the order of some kilometers. In our design of the instruments, we considered as a target objective to reach 9 kilometers in depth. Now, what we'd like to do with the RIME in terms of science is to contribute to some of the relevant science objectives of the full mission. Of course, we are in a condition on the basis of what I have presented before to analyze what is happening in the subsurface of the 3 icy moons. We are, as you know, the JUICE mission has the orbital phase around Ganymede, which is the phase that will allow us to acquire a large amount of data, and so to characterize what is happening on about 30% of these icy moons. The radar will contribute significantly to characterize the ice shell. You have seen some example on the kind of information that we can get. We can get information on the subsurface structure, but also on the different attenuation that different impurities, for example, in the ice can generate. And of course, this kind of system is able to detect the possible presence of a pocket of water in the subsurface. We are not targeting with a sounder the detection of the interface with the ocean, but we are targeting the possible detection of pocket of water close to the surface. The science objectives are interesting, very interesting also for Europa and Callisto. I'll show later what is the plan for operation of RIME. On Europa, we have a couple of flyby, but in very interesting area. And on Callisto, we have many flyby that will allow probably to get very relevant data for the characterization of the subsurface. Just a nice illustration of what is expected on Europa. This has been prepared by the colleagues of NASA JPL, and this is prepared for illustrating what will be the target of the Europa Clipper mission. But I think this illustration clarifies quite well what a sounder can do if you connect this with what I have presented before. The possible model for Europa is to have the crust of ice on the top of the ocean, and then the ocean on the top of rocks. But clearly, the structure and all the different possible pocket of water that can be present in the ice sheet becomes extremely interesting as target for a radar sounder, because we have the capability to identify all this kind of structure, of course, taking into account the properties of the system. On Ganymede, we don't have this kind of, the model, as you know, is different. We expect the ocean is a larger depth, and we expect that we have the ocean between ice. But there are many interesting, important science objectives that are connected with the understanding of what is happening in the subsurface. Here, I don't have, of course, the time to enter in the details of what is planned in terms of science objectives, but we have analyzed in detail all the possible contribution that the detection of the features in the subsurface can provide, in overall then to the JUICE mission and to understanding of the icy moons. Of course, we'll have the capability to compare what we see in the subsurface of the 3 icy moons, and this is, again, extremely interesting because let's say that this is, as you know, the first time that a system like this, a radar like this, is exploring the icy moons of Jupiter. So all the data that will be taken will be extremely exciting, I guess, in terms of understanding of what we have in the subsurface. Okay, just a few examples coming from the images that we have from the previous mission. We have data from Voyager, from Galileo, that represent the surface of Ganymede, where, you know, we have the younger parts that are related to the brighter terrains. We have the more ancient part, which is related to the dark terrains. We target many different kind of features on the surface of the planet. This is an example of an area that will be covered by RIME in the acquisition, where we have many different features in the surface that require analysis in the subsurface for better understanding. Here we can see the dark terrains between the Marius Regio and the Galileo Regio that have in the middle the bright terrains. We have Faro in this area of the surface of the planet. We have palimpsest, a lot of different features that require analysis of the subsurface to have a proper interpretation. For example, understanding better what is happening on a feature like this in the central dome crater Melkart, where the formation is associated to many different possible hypotheses. This can be generated by the refreezing of the ice after an impact, or this can be generated by post-impact diapirism, or this could be just the results of uplift of material at the time of the impact. Looking at the subsurface and the possible interfaces that we see in terms of material in the subsurface will help to understand what is the genesis of this kind of features and to clarify what is the process that is behind the generation of these features. Other examples are connected to the capability to explore what is happening in the Patera. Patera are scalloped depression, and these areas are expected to be an area where we may have cryomagmatism. And so looking at the images, what we see is that we have that the morphology of the Patera as the presence of apparently rigid deposit. When you look at the topography that you have in the Patera, the topography that you have in the surrounding group terrain, you see similar kind of behavior. So it will be extremely interesting to look at the interfaces that you may have to clarify what is the process behind this and if this can be connected with the cryomagmatic reservoir in the subsurface. Okay, these are just some examples. Just to give you a better idea of the instruments, this is the data sheet of RIME. We are operating at a central frequency which is of 9 megahertz. The data that I have presented before from Earth observation usually were acquired at about 60 megahertz, 40, 60 megahertz. So we are at a lower frequency because we'd like to penetrate deep. Say that our target I was mentioning is 10 kilometers. We can acquire data with a vertical resolution that can be 50 or 150 meters, more or less, in the ice. And this is associated with the use of two different bandwidth for the sounder, 1 megahertz or 2.8 megahertz. We are in a condition in which we can use the azimuth processing for the radar, which means that in the long track, we can control the resolution, the horizontal resolution, to values that are quite small, up to 1 kilometer. And whereas in the cross track, we have a resolution that is a little bit smaller. And if you look at the power that is transmitted, our peak power is less than 10 watt. But with 10 watt, we expect to penetrate, since the ice is very cold, to the 9 kilometers that are in the baseline. Okay, a couple of words on where we expect to operate. You know what is the mission profile of JUICE. I don't enter in detail, but during the Jupiter tour, we are in a condition in which we expect to operate in the flyby that we'll have on Ganymede, Callisto, and Europa. We are in a condition in which we can optimize our performance when we are below 1,000 kilometers to the end. So we can operate between 1,000 kilometers and the closest approach during the flyby. And then we will have operation on the circular orbital phase on Ganymede at the JCO 500, and then at the low altitude circular orbit that now is back in the baseline, which is extremely interesting for RIME. That will be at about 200 kilometers. There is still a discussion on the real altitude of this orbit. Now, if I show you some more details, I don't enter in the details of the single flyby, but we are in a condition in which in the different flyby, what we can do is to program the radar in different ways, because we have to take into account the velocity of the spacecraft, the uncertainty of the orbit, and so on and so forth. I think it's quite interesting to take a look at the trajectories that are associated with a different flyby and to the time in which RIME is expected to operate. I was telling you, below 1,000 kilometers, these are the two tracks that we expect to cover on Europa, at least at in the presence baseline in very interesting areas. These are the tracks that are connected with the flyby that we can get on Ganymede. And these are the tracks that are associated with the flyby of Callisto. You can see that we have many tracks that are, let's say, almost parallel with some cross. This is extremely interesting for the capability then to understand more on the structure in the subsurface of these areas. Well, I mentioned we have then the circular orbital phase, which is something that will allow us to have a full coverage. We plan to have 30% of coverage of Ganymede with acquisition that have a track-to-track distance of about 50 kilometers. So a very good representation of many different interesting parts of the icy moons. We also plan to have other acquisitions, sub-Jovian, on interesting targets. But this plan to operate anti-Jovian point out one of the challenges that we have in the Jupiter system with the sounder, because as you probably know, we have that the Jupiter radio emission is quite consistent. We have non-thermal Jovian radio emission that are associated with a density power which is very significant, much higher than what is the usual galactic noise, which is the noise that is used for the design of this kind of system in terms of signal-to-noise ratio. Below 40 megahertz, we are in the condition in which this noise can be present in the data, and so this can affect the acquisition of the sounder. Fortunately, the noise is sporadic, and so we expect that these bars are not always present in the system. So with the operation, what we do with RIME, this is a very simple illustration. Don't take the geometry as a reference. Of course, this is just an illustration. But what we do with RIME is to transmit our electromagnetic wave for taking our measurements. And if there is a noise, we are in the condition in which we have interference. So when possible, we prefer to have our acquisition in the anti-Jovian part of the orbit so that we can avoid the interference of the Jupiter noise and acquire our data without the risk to have the presence of this sporadic noise. However, we have also the possibility to acquire when we are in subjovian, because the noise is sporadic, and also because we implement on board the possibility to have what we call the passive sounding. That is, we can use the Jupiter noise as a source of opportunity and correlate the measurement of the noise and the reflection of the noise that comes from the subsurface of Ganymede in this example. And so we are in the condition in which we can try this kind of experiments to get data in a different modality without using our transmitter. We did a lot of studies on what we can expect in terms of the presence of this Jupiter radio emission. We have done analysis on the data acquired by Juno, by the Juno wave instruments, trying to understand what is the occurrence of this noise in that data in the portion of the spectrum that are relevant for us in the surrounding of 9 megahertz. Also trying to get more understanding on the location of the noise. We know that the noise is beamed, and so it's important also to be able to understand the prediction between the occurrence of the noise and the possible location of the noise. We know these data are quite interesting. Of course, Juno waves has not the sensitivity to understand everything, and so we'll learn then more when we arrive in the Jupiter system. Okay, just a couple of words before then showing you the first data that we have acquired and going to the conclusion. I was mentioning that there are two radar sounders that are now in the cruise to the Jupiter system. We have also Reason, which is on board of Europa Clipper. Rime and Reason have been designed at the beginning of the idea to have the mission with a similar concept, because they were designed in terms of concept at the time of the AGSM Laplace joint mission. At the beginning, in 2008, there was the idea to have a joint mission, as you probably know, between ESA and NASA, and there were in the mission the plan of 2 orbits, one for Ganymede provided by ESA with Rime on board, and the other one for Europa with provided by NASA with Reason on board. What happened is that when you look at the acquisition mode of the 2 instruments, there is one acquisition mode which is exactly the same. We transmit a 9 megahertz central frequency with a bandwidth of 1 megahertz, and this is the same for Reason. Translated, this means a vertical resolution in eyes of about 140 meters. This is the deep penetration mode that should arrive at 9 kilometers, maybe more on Ganymede, depending on the condition of the ice. And then on the Rime, we have another mode that allows to have deep penetration or shallow, depending on how we program the instruments, with a resolution of 50 meters. On Reason, the other mode is operating with a central frequency of 60 megahertz and a bandwidth of 10 megahertz, which means translated in eyes 40 meters of resolution. This is a mode that has a shallow penetration. So let's say that the 2 systems are complementary in terms of then the operation of the different mission, but they share some common measurements that becomes extremely interesting then for creating, let's say, data set that include the measurements of both the sounder for understanding more in general on the icy moons. We have also some possibility to have probably intercalibration in some specific area of acquisition. By the way, the radio frequency part of Rime has been provided by JPL, and this is based on the same kind of hardware that is flying on Reason. Okay, I'd like to conclude my presentation presenting some the data that we have acquired up to now with Rime. You may have heard that there are some interference from the spacecraft that disturb the sounder what we have done in the first phase of the cruise was to develop algorithm that can take under control this interference, mitigate interference, and construct properly the radiograms that are taken by the instruments. This is the first example, the first radiogram that we have generated in the first opportunity we had, that was in the flyby of the moon. Of course, the sounder needs a target. We transmit our electromagnetic wave, and the first target of the mission was the moon. You can see here the representation of the surface of the moon taken by RIME. These are data that are not yet focused, are just range compressed. And what you see here is the surface. This is the representation on the digital elevation model of the trajectory of JUICE, and this is what we get. Take into account that, of course, we see just the surface and the clutter due to the off-nadir echoes, because we are in a condition in which we transmit just less than 10 watts. And this is not enough in this area of the moon for getting penetration. By the way, if you look at the topography, we are moving from -6 to +6 kilometers, so extremely rough area, which is not good for penetration with the sounder. The sounder that operate on the moon transmit 800 watt as peak power, so completely different kind of power. And this is the results of the fully focused data, which represent, again, the surface on the same area. In this case, what is changing is that we have also the azimuth compression. And so we have increased the resolution and we have the representation of the surface. Again, what you see in this area, like in this portion where we have the Pasteur crater, is not something which is due to the subsurface. It's just related to the off-nadir echo that comes with some delay to the receiver, and so are mismatched as a contribution from the subsurface. If you are expert or you are familiar with the sounder, you know that in order to reduce the ambiguity from the clutter and the real subsurface feature, you need to have a digital terrain model in order to simulate this kind of effect that can be perfectly reproduced when you have a digital elevation model. This is just another example that zoom a little bit more in detail of this part of the trajectory on the focus data that point out anyway that the sensitivity of the sounder to the different condition on the surface. We could assess that the quality of the data is very good. RIME is baseline in terms of performance, and this despite some interference that are generated by the spacecraft. Final example is this that represents what we have in the measurements that we have done on the Earth. We did not operate the transmitter on the Earth. What we did was just to listen. The radio frequency noise coming from our planet. What you can see here is the spectrogram, the different frequency in which we operate in the measurements with the RIME. And what you can see here is the time of the flyby. There are many different components that have been detected. We have also some scan that have been done for the different frequency that are associated with the instruments that are used for sounding the ionosphere from the ground. And all these kind of radio sources are interesting for us because we can try to have a kind of calibration by relating what we measure with what has been the signal that is transmitted. We plan to have more of this calibration for the next flyby of the Earth. So I come to the conclusion of the presentation. What I have presented here is, let's say, the experience that the community has developed for sounding the ice on the Earth. The experience that pointed out the capability to analyze many different scenarios that are extremely important then for decoding the data that we'll get on the icy moons. So let's say that we are in a condition in which this experience will lead us in terms of interpretation of the data. But on the other hand, if you look at from the perspective of Earth observation, all the experience that is gained from spaceborne system flying on a celestial body, included JUICE and RIME, is becoming very important then for implementing a mission based on a satellite for studying in a more systematic way what is happening in the polar area of the Earth. Of course, this means that, we are in a loop in which the experience on the Earth helps a lot for the interpretation of the data on the icy moons, but experience on space of a mission like JUICE will help a lot in developing a sounder system for Earth observation. Okay, that's all. Thank you for attending this webinar, and of course, I'm happy to answer your questions.
Thank you so much, Lorenzo, for this excellent talk. We already have a couple of questions that were popping up during your talk, so I suppose we just go straight into them. The first question was by Avishek Ghoshal. I hope I pronounced it correctly. Can you please suggest some resources through which we can learn more about SAR data processing and interpretation?
Okay, there are many books. When you say SAR data processing, there are many textbooks that address this kind of topic. Let's say that typically they are more focused on imaging rather than on sounding, but the concept is extremely similar. So the processing that you are doing, range compression, azimuth compression, is similar between what you do when you perform imaging with synthetic aperture radar and when you perform sounding. Of course, there are some differences, but let's say that if you refer there are many textbooks, so I cannot point to one, but if you refer to that, you can get all the background, and then you find, a lot of literature in terms of paper that address this for the sounder part.
Okay, I hope that answers the question. There is, I guess, more of a comment by Jan-Peter Muller. There is a P-band radar which is capable of subsurface sounding called ESA Biomass, which is producing a global data set at 200 meters. I guess 200 meters.
Yeah, this is true. This is a recent mission launched by ESA in 2025, but this is not expected to arrive to the bedrock. This is extremely interesting indeed. This has been developed as the name of the mission say, biomass, for studying mainly the forest and the biomass of the forest. But there are extremely good opportunities for taking data on the icy areas. But we are at 460 megahertz, which means that, we can get very nice data on the subsurface, but it's difficult to reach the bedrock. Indeed, the mission that are studied for reaching the bedrock are operating at 40, 50 megahertz in order to get the penetration that is required. But for sure, biomass will help a lot to get additional data on the ice, even if, the ice is not the main mission objective.
Mm-hmm. Yeah. Get some serendipitous data there, maybe. Yes. A question by Tara Marie Brundel. What is the minimum orbits around Ganymede that is needed to fulfill the nominal science objective for RIME?
Well, the number, you mean the number of orbits, the altitude of the orbits? What?
The minimum, I guess, yes. Minimum number of orbits.
Let's say that what we expect to do is to get a coverage, which is a coverage of about 30% of Ganymede. And you should take into account that when I say the coverage, I'm considering a track-to-track distance in the order of 50 kilometers. So on 30% of the planet, we will have a track-to-track distance taken from the profile of the sounder of 50 kilometers. So, and this is what is our baseline for getting the science objectives on Ganymede.
Okay, the next question is by an anonymous attendee. What is your strategy for a cross-track clutter discrimination?
Well, that's a very good question. Let's say that indeed we are expecting to leverage on other instruments that are on board of JUICE for the construction of the digital elevation model. This is something that can be done by using Janus, by using GALA, the laser altimeter, and the imaging system. And this will help to generate a digital elevation model for Ganymede and to get some data that can be relevant for the flyby. On the flyby, the story is more challenging. We have anyway the capability to leverage on signal processing for discriminating, at least partially, the clutter from the subsurface. But the goal is to optimize acquisition with other instruments to get the information that help us to simulate then the effect of the surface.
Okay, I hope that answers the question well. Another anonymous question. How will the refractivity of the upper surface as a function of depth be estimated?
Well, let's say that the reflectivity is quite interesting parameter to measure, indeed.
Sorry, it says refractivity. The
okay,
refractivity. So how will the refractivity, not refractivity of the upper surface as a function of depth be estimated?
Okay, let's say that we are in the condition in which what we can do is to analyze the different possible conditions that we'll have on the surface and the subsurface in order to discriminate the different contributions that comes from the interfaces that we'll have in the subsurface. Then, depending on the condition, depending on the condition of the ice, also the impurity of the ice, we'll have to understand how making this kind of analysis.
Okay. Then Sabatino Santagello asks, is it possible to obtain data along the across-track direction using a purely nadir pointing radar system? And if yes, how?
Well, it's possible to get across track. Let's say that this is something that we have done in the past with the data acquired by other mission. In particular, we try to do that on the data acquired on Mars. So you can try to let's say identify in what is the contribution which is of nadir that is associated with the clutter. Let's say the contribution that comes from positions that are not orthogonal with respect to the spacecraft. We have also, if there is interest, write to me that we have also a paper on this, and so I can point to a reference that clarify how this can be done. It's a little bit a structured process, but at the end, yes, you can try to do that because you can anyway try to get information.
Okay, Sabatino, thanks you. Amazing, thank you.
Okay. Write me an email and I'll give you the pointer to the reference.
All right. Another anonymous question. Does Saturn also have sufficient decametric radio emissions for a passive sounder around Saturnian moons? Are there any key differences with respect to the Jovian decametric radio emissions that must be taken into account, or that should be taken into account?
Well, that's a good question. I'm not sure. I don't know in detail the characteristic of this radio emission, so I cannot answer in detail. Of course, the concept of passive radar is something that has been experimented on the Earth, and so has been proven that this works. What we can really get then on the Jupiter system will be more clear at the time in which these experiments will be implemented there. Yeah, there are a lot of factors, the geometries of the noise, the position between the noise source, the spacecraft, and so on and so forth, that should be evaluated. And so, let's say it's a very interesting way for performing experiments. I would not say this is something that we can think as a baseline for performing measurements on other systems. But I cannot answer on the part of the difference between the noise because I'm not familiar with the Saturn systems.
Okay, excellent. There's three more questions, I see. Mauro Pirarba is asking, how challenging is the interpretation of data and how is AI changing this?
Interpretation of the data is very challenging, okay, because unfortunately, one of the limitations of this radar is that they are ambiguous. Okay, let's say that we have a different condition that can generate, let's say, a similar response of the radar. So when I look at the interface, I see the interface, but it's not obvious what is the reason for getting this kind of interfaces. If you follow, for example, the discussion on the water of Mars, there has been a lot of interpretation on the possible reflection from the subsurface. So this is something that is challenging. But AI can help, of course, because on the one hand, it can help us to process systematically the data and to avoid that we miss something because there is not the analysis done on all the data that have been acquired. On the other hand, we have the capability to use AI and Earth observation data in order to teach the system to perform a more quantitative analysis systematically. So let's say that we expect that what we learn on the Earth can be used with proper tuning for understanding what is happening on other celestial bodies, in this case on the icy moons. So this is something that I expect will help. Also because the methodology, the technology that we have now of AI is extremely advanced and can help for sure for this kind of analysis. The analysis will be done after 2032. So let's say that we'll see other evolution, and I'm quite confident this will be a key part of interpretation of the data.
Okay, let's have two more questions and then we'll close the session. Daniel Lecora asks, is there a possibility that the Stratus mission could detect or map subsurface cavities on Earth, such as lava tubes, for example?
Okay, good question. That would be something possible. Take into account that the vertical resolution of a sounder like the one that I just mentioned on Stratus is 10 meters. So we are in a condition in which this is something that is probably possible. This detection of the lava tubes is in a completely different context, is targeted, for example, on Venus, where, of course, we don't have the ice. But potentially this is something that could be considered.
Okay, and the final question for today is by Edwin Francisco Valdes Arias. What type of metrics you use for the identification of some characteristics of the subsurface, such as salt layers, for example?
Okay, we need to understand what is the attenuation that we have, what is the reflection that we have, and we need to relate then the reflection to the two components. One is the composition. The other one is the roughness. Okay. Usually we have ambiguity in the echo that we receive because the reflection is affected by the two components, the composition and the roughness. So we can analyze the strength of the echo and the attenuation that we have in the subsurface and try to analyze the coherence of what we get in order to separate what is associated with, let's say, the rough behavior of the interface and what is associated with the component.
Okay, thank you so much, Lorenzo. So have a great time, everyone. End of the year time, and see you very soon next year.
Thank you. Bye bye.
Thank you. Bye bye.
Thanks, everybody.
Thank you.
Bye-bye.
Bye bye.